Hi everyone. So the purpose of this video is to go over the first page of Midterm 2 for Chem 3A, which is Chemical Structures and Reactivity at UC Berkeley. This is in fall 2019, taught by MaryAnn Robak. So here we go. So the first question of the second midterm is asking you to assign the configuration for this spot right here, this carbon. And so first, let's double check that it is a stereocenter. So there's one implied hydrogen that's going to be right behind that oxygen right there because there's two in plane bonds and there's one that's wedged. So there's going to be one that's dashed, and that's what the implied hydrogen is going to be on. And so as you can see, we have this benzene group as one substituent on the carbon. We have the hydrogen, we have this oxygen, and leading to the benzene and then the alkoxide, and then we have down here this other ring shape with the amine and the oxygen. And so it is in fact a stereocenter. There's 4 different priorities, and so now we have to decide the priority numbering for each of these. So hydrogen is going to be number 4 priority. Okay, yeah, that's just going to be number 4 almost always, or I think always. This oxygen over here is one of the substituents, and then both of these right here are carbons. And so oxygen is a higher priority than carbon, so that's going to be number 1. And then we have to look at what each of these carbons here are connected to, because they're both carbons. So then we have to look at what they're connected to. So this one down at the bottom is connected to an oxygen. It's connected to a hydrogen right here. And it's connected to this carbon. So those are the 3 other things that it is connected to besides the bond that we're coming from. We're not going to count that carbon that's above it. I guess we could, but we'd have to count it for everything, and that's not really necessary. And then we're going to look at the other orange carbon that's connected to carbon with the sigma bond. It's connected to the same carbon again with a pi bond, and then it's connected up here to another carbon with a sigma bond. So it's connected to carbon 3 times. So we're going to say that's C, C, C. And so we're going to look at these 2 things that they're connected to, and we're going to decide which one has the higher priority. So this one has an oxygen, and oxygen beats out carbon, and so the carbon that's connected to the oxygen is going to be the higher priority. So this is going to be number 2, and then this last one's going to be number 3. So now we've decided what each of the priorities are, so let's erase all the other information, because now we need to figure out whether it's R or S as a configuration. We don't need this hydrogen here. Okay, we just need to know which one's 1 through 4. And so this problem is a little bit easier than it could have been because hydrogen is already, the 4th priority is already on the dashed line, and it's already in the back. So we don't need to rotate anything or like redetermine, because we want to draw an arrow from 1 to 3, but with number 4 in the back. So we can already do that. We don't have to do any rotation or anything. We just draw an arrow going from 1 to 2 to 3. Okay? So now we need to decide whether this is R or S. So the way that I do it, there's many ways to determine whether it's R or S, a lot of tricks that people use. But the way I do it is I look at the curvature of R and S. If you're going to draw an R, you draw this line, and then you draw this curve, or at least that's the way I draw R. And so this curve is shaped like this. Whenever you write it, you draw it like that. And so that is the shape of R. You just look at that curve right there. And then an S, you draw starting with this curve and then going down. And so if we're just looking at the beginning curve, that's what looks like an S. And so this way is R, and this way is S. You can also just remember that R is clockwise and S is counterclockwise, but I don't like having to memorize things, and that can easily get switched up in your head. And so that's the way that I recommend doing it, is just by looking at the curve. If that doesn't really work for you, or you don't see it, you can look up other ways to determine R or S. But that's the way that I'm going to use it. And so if we look at this curve that we drew up here, let me highlight that in green. If we're going to draw either the letter S or R, we can see that this curve, the way I drew it, is the beginning of an S, right? A little bit of a squiggly S, but an S. So that's going to be the S configuration. Yeah, so now we move on to the next one. Over here, again, let's double check to make sure this is a stereocenter. So we're going to draw the implied hydrogen here. It's again going to be behind the oxygen because there's one implied hydrogen and the oxygen is on a wedged line and there's no dashed line, so the hydrogen has to be on the dashed line. And then what four things is this carbon connected to? It's connected to one hydrogen, right? That's what we just drew in. It's connected to an oxygen. It's connected to a carbon, which is connected to a nitrogen, and it's connected to a carbon, which is connected to an oxygen. So those are all four different groups. So we know that we can decide whether it is R or S. It is a stereocenter. Okay. So now let's determine what the priorities are. So hydrogen, again, is going to be number 4. And then we have the choice between a carbon, and an oxygen. So oxygen is going to be number 1. It's higher than carbon. And then we have to look at what these two carbons are connected to determine which one is number 2 and which one is number 3. So this carbon up here is connected to an oxygen, an implied hydrogen, and the carbon right here for the benzene ring. And down here, with the other orange priority, it's connected to a nitrogen and 2 hydrogens, right? It's only making 2 bonds that we can see, so there's 2 implied hydrogens. And so which one is a higher priority? That would be the one with the oxygen, because oxygen is higher than the highest priority here, which is nitrogen. And so the carbon that's connected to oxygen is going to be higher than the other one. So this is going to be number 2, and this one's going to be number 3. Okay, again, let's erase all the unnecessary information. We just need the 1 through 4 to determine whether it's R or S. Let's see, is that everything? Yeah, so we've got 1 through 4. Again, it's convenient. MaryAnn wrote it so that the 4th priority was already in the back, so we don't have to do any rotation or flipping in our head. So we are just going to draw an arrow from 1 to 3. And then again, I imagine myself drawing an S or an R, and in this case I would be drawing an S, and so this is going to be an S configuration. What were the other options for this question besides R and S? There was E, Z, or none. So none would be the case if it wasn't a stereocenter, as in if 2 of the groups that the carbon was connected to were the same, or if it was only connected to 3 groups, that wouldn't be a stereocenter. So that would be the case where it's none. And E versus Z would be if we were looking at an alkene, but we're not in this case. We're looking at just a carbon that's making 4 different bonds. So yeah, so these are both S. The second question, 1B, is asking, so it says that the structure above shows the stereoisomer that's more biologically active, but the medication is sold as a racemic mixture. So what does racemic mixture mean? That means that that the 2 different stereoisomers that we're considering are found in equal amounts. or they're equally likely to form. And so that's usually the case with enantiomers. It can't really happen with diastereomers because with diastereomers, something could be positioned closer to something else, and then you would have more Gauss interactions or something. So racemic mixture is really just something that you would consider for enantiomers, not for diastereomers. If diastereomers are formed, it's usually not a racemic mixture. If enantiomers are formed, then it is a racemic mixture. So if it's saying to draw one stereoisomer that is part of the racemic mixture on the left here, that means we're going to want to draw the enantiomer of the one above. And so the one above had two wedged lines. Let's see, let's double check to make sure it all looks the same besides the stereochemistry, and it does. It looks the same as both of these. We just need to draw in the stereochemistry. And so since both of the lines were wedged above, they're both going to be dashed here to the oxygen. That's the easiest way to draw it. I guess you could try to do something else, be more creative, and draw the dash to a different priority group, but this way is more conventional, just based on the problem above. And you can double check to make sure that this is the opposite stereochemistry, because since both of those groups were S above, we want them both to be R below. And so again, oxygen's number 1. There's now going to be a hydrogen in the front. And then the carbon that's connected to 3 carbons versus the carbon that's connected to an oxygen and a carbon and a hydrogen. This is going to be number 2, and this one's going to be number 3, and the hydrogen is number 4. So in this case, if we draw the arrow 1 to 3, that looks like an S. But since the 4th priority, right here, this hydrogen, is coming out in front of us, we have to flip it, and it will be an R. We don't really need to do that for this problem. We are already shown that the mixture, the molecule is already the same as it was drawn above. So you really don't need to check the stereochemistry. You just need to invert it, which just means to draw the 2 dashes. But, that's just something to double check if you have some time during your exams. Okay, so then it says, draw a stereoisomer that is not part of the racemic mixture of reboxetine. And so the stereoisomers that were part of the racemic mixture were the enantiomers. And so now we can draw either of the diastereomers of the one above or the one that's next to us, and that will be the ones that are not part of the racemic mixture. So to do that, we can just make one of them dashed and one of them wedged, and that'll be another stereoisomer that is not part of the racemic mixture. You could also do the opposite. You could, let's just do it in blue. You could make this one wedged and this one dashed. You just can't do them both wedged or do them both dashed, because those are both part of the racemic mixture above. Okay, so the last problem on this page, it says classify the relationship between each pair of structures and note the top structure in each pair matches the structure from part A. So that means it's going to have the same stereocenter. So let's go ahead and include that. They're both S in part A. Actually, let's just keep it on blue. So let's just label that as S. That might come in handy when we're checking it with the bottom ones. Okay. So what are the options of the relationships? They could be constitutional isomers, enantiomers, diastereomers, or identical. So right away, I'd say constitutional isomers is the one that's not like the others. The other ones are all stereoisomers, but this one's, or those are configurational isomers, you could also say, but the constitutional are different. So constitutional will stick out more because they're going to be connected differently. Atoms are going to be connected in a different arrangement, versus enantiomers, diastereomers, and identical. The same atoms are going to be connected to one another, but they're just going to be connected maybe in a different orientation. So first, let's just double check to make sure that these first two aren't constitutional isomers, because that would stick out the most and that would be easiest to identify. So let's just double check. So we've got this this 2 carbons and then the oxygen. That's the same as over here. And we've got that connected to the benzene. And then 1 carbon away from that is the oxygen here. That's the same thing here. It's only 1 carbon away. And then this oxygen here is connected to a carbon, which is then connected to the benzene and this group. This oxygen is also 1 carbon away from the benzene and this group. And as we can see, that in this group here versus this group, the oxygen is just 1 bond away, and the NH is 2 bonds away. So overall, they're connected. Let's just erase. They're connected the same way. So they're not going to be constitutional isomers. Constitutional isomers would be connected in a different order or something along those lines. Maybe this this alkoxide would be right here instead. That would be an example of a constitutional isomer. But that's not the case. They're all arranged in the same order. So now we are going to check if, so we know that it's not constitutional isomers. Now we need to check if they're enantiomers, diastereomers, or identical. So the easiest way to do this is to check the 2 stereocenters, here and here. If they are the same, then they'll both be S. That would be identical. If they're enantiomers, they're both going to be the opposite. Sorry, that's ugly. Enantiomers would both be R and R. And then diastereomers would be kind of between enantiomers and identical. They're not exactly a mirror image, but they're also stereoisomers. And so it would be like 1 is R and 1 is S in either order. So let's just check the priority. And we're going to ignore the dashes and the wedges as far as like just trying to figure it out intuitively, because this could just be flipped over. It could be identical even though it doesn't look necessarily identical the way it's been drawn. So we're just going to figure out what the priorities are. Okay, so we know that this carbon here has to have a hydrogen that's implied. And so because we have a dashed line and 2 in plane lines, our hydrogen is going to be on a wedged line coming out in front. And that's going to be our 4th priority. The oxygen is always our first priority. Then we have the carbon that's part of the benzene. It's connected to 3 carbons, carbon, carbon, carbon. And we have the carbon that's connected to oxygen and carbon and hydrogen. So again, this one's going to be number 2 priority. This one's going to be number 3. Let's erase these. Just need to note that it's 1, 2, 3, 4. Okay. So we're going to draw, so the 4th priority is in the front this time, which isn't too bad of a problem. It's not as hard as if it was on a in-plane line. And so what we're going to have to do is we're going to draw a line from 1 to 3, or a curve from 1 to 3. We're going to figure out what that looks like, what the curve looks like, and then we're going to switch it because the 4th priority is in the front instead of the back, so we're just looking at the opposite. So let me point this out. If the 4th priority is on an in-plane line, it's not as easy as just like drawing the curve and then switching it to the opposite. You actually have to move the 4th priority so it is on a wedged line or a dashed line, so it's in the front or the back, so that you can actually determine it. You can't really just like have a clear and cut rule for determining if it's if you switch it or not, if it is on an in-plane line. You actually have to think about rotating it. But that's not the case here. Let's just draw that curve from 1 to 3. Oh, from 1 to 3. So if we draw, that's like an R, right? There's this curve here. That's like the R curve. And so that would be an R, but like we said, the fourth priority is in the front, so we're going to say it's the opposite, so that's an S. Nope, an S. Okay, we have to figure out the stereochemistry of this next carbon, so let's erase everything except for the S, or let's just draw on the S again, because we don't want all of that priority to get in the way. So again, we just determined that this one is an S. And now we have to figure out this carbon. So it's connected to an oxygen here. It has an implied hydrogen right here next to the kind of amine group. And then it has this carbon connection and this carbon connection. So this carbon is connected up here to oxygen and carbon and hydrogen. And this one down here is connected to nitrogen and two hydrogens. So like we've done a bunch of times in this video, the oxygen is the higher priority over the nitrogen. And so the carbon that's connected to that oxygen is going to be the higher priority. So like we said, oxygen is number 1, hydrogen is number 4. The carbon that's connected to oxygen is number 2. And this one connected to the nitrogen is number 3. So let's erase everything else. Okay, so we're going to draw an arrow curved from 1 to 3. And let's look at this curve. Again, that's like what we would draw for an R, right? So that would be an R, but our fourth priority is in the front, so we're going to switch it again. That's going to be an S instead. And so both of our priorities are S. Let's figure out what that tells us. They're both S, and above they're both S, and we know they're not constitutional isomers. So then out of identical enantiomers or diastereomers, they must be identical since they have the same stereochemistry. If it was opposite, it'd be enantiomers. If it's partially opposite and partially the same, it'd be diastereomers. But that's not the case here. Let's move this out of the way. Okay. So now we're looking at this one. Again, first let's determine if they are constitutional isomers, because then we don't have to look at the stereochemistry. We can just look at the connectivity and move on. So we have this carbon here and this carbon here. Let's look at what they're connected to. So this carbon here is connected to the oxygen. Let's just follow it along with a highlighter. It's connected to the oxygen, which is connected to the benzene, and then one carbon away, it's connected to the epoxide with the oxygen and then the ethyl. Here it's the same thing. There's this carbon is going to be the same as this one. This one is the same as this one. Where it's connected to the oxygen, the benzene, and then one carbon away from that is the epoxide with the ethyl. Okay, so that's the same. Then they're both connected to the other stereocenter, which is connected to an oxygen, and then a carbon and a nitrogen. That's over here, up here, the same, oxygen, carbon, nitrogen, and then it's all in a hexagon shape. There's 2 carbons between the oxygen and the nitrogen. So that's the same. Okay, let's look at the last thing that the purple carbon is connected to. They're both connected to a benzene. Okay, so everything is connected in the same order. So that means that they are not constitutional isomers. We can determine that right off the bat. So now we have to look at the stereochemistry since they're not constitutional isomers. Okay, not constitutional isomers. So we're looking at stereochemistry. Okay, so let's determine each one. Let's first determine the one on the right. So it's connected to an implied hydrogen in the back. It's going to be fourth priority. Oxygen is going to be the first priority. We've got the carbon that's connected to the nitrogen and the hydrogens. And we've got the carbon over here, the other stereocenter, that's connected to the oxygen. So we have already determined this before. This one's going to be the second priority, and this one's going to be the third priority. Then if we draw the arrow, it's going to go from 1 to 3. It's making that shape. That's like an R, right? You draw like that. So that's going to be an R, and the hydrogen's in the back, so that is really an R. We don't have to switch anything. So let's erase everything else, and let's just call this an R for the stereocenter right here. So now we're going to determine this one. So we already know that they are not going to be identical because one of the stereocenters are an R. And so regardless of what the other one is, it is not identical. But if the other one is an R, it's going to be enantiomers because they're both going to be opposite. And if the other one's an S, then they're going to be diastereomers because one of them's opposite and one of them's the same. So let's determine the stereochemistry. There's a hydrogen behind the oxygen. Oxygen is going to be number 1 priority. Hydrogen is going to be number 4 priority. Then we've got the carbon over here that's connected to oxygen and carbon and hydrogen, OCH. And we've got the carbon over here that's connected to 3 carbons. So again, OCH carbon is going to be the higher priority, so that's going to be number 2. This one down here is going to be number 3. Let's erase the rest. So then if we draw an arrow from 1 to 3, 1 to 2 to 3, I should say, that's going to be in an R shape. And the 4th priority is in the back, so that really is an R. We don't have to switch anything. So both of the stereocenters are R. So that's going to be enantiomers because both of the stereocenters in the molecule are switched. One thing I forgot to mention is if there were any other stereocenters in this molecule, we'd have to consider those too. There aren't any in this molecule. You could double check that. You could check each atom and make sure they're not a stereocenter. I think I did that during the test, but yeah. So if there were any other stereocenters, you'd also have to consider that when determining if it's R or S, or considering if they're enantiomers or diastereomers or identical. But in this case, we're only looking at these 2 stereocenters. Okay, so last one. We're first going to determine if it is if they're constitutional isomers, because that'll be the easiest. We don't have to consider the stereochemistry. So let's look at each of the stereocenters. There's one right here, there's one right here, and there's one right here, and there's one right here. And so you might already be thinking it looks funky. That's what I'm thinking right now, because if you see this stereocenter right here, that should match with this stereocenter here, right? Because these 2 match. As far as connectivity goes, they're both connected to the oxygen, then the benzene, then the epoxide, and the benzene on the other side. That's what it's connected to up here, the benzene on one side, and then the oxygen, the benzene, and then the epoxide, ethyl epoxide, everything. So those 2 match. So the yellow one should match too. But the thing is that this stereocenter up above is connected right to the oxygen, but this one below here is connected right to the nitrogen, and it's 1 carbon away from the oxygen. So right off the bat, there's different connectivity. We don't even need to look at the stereocenters or the We don't need to classify whether it's R or S or not because right off the bat they're constitutionally different. They're connected to different things. So they're going to be constitutional isomers, not configurational. And so that's the first page of midterm 2.